just die on me. So okay, I guess first thing first, for what we discussed last time and also regarding with the homework, I guess I mentioned that if you remember, we have the essential matrix that last time we discussed essential matrix that if you multiply from the left view point or like points, 3D points from the left view in the Cartesian coordinate and the point in the right view, maybe I write it this way and then put transpose here, out here, then multiply with the right view, the points from the right view, also in the Cartesian coordinate, that should give us 0 here. And in our derivation, we basically take this E as like R Tx here, or T cos here. T cos is like the matrix representation of the cross product. Remember that like, if I have T cos Y here, that basically should give me T cos Y basically. So it's like this matrix T multiplied by Y should give you a vector, right? So this should just give you the vector T cos Y. And I mentioned that, okay, I guess I don't have time to elaborate last time. So some books, actually many books, expand E as some T, maybe I use a different notation, T pi cos R instead. So both are correct because you can see I can, depends on how I decompose that. Of course, this will be a different T here. So the R here, by the way, will be the same, but the T will be different. Actually, it turns out that this T here should be just equal to RT here. So I will quickly show why is that. So think of like I have to start with, let's say, I will argue first, like if I have RT here, I might consider this RT cos matrix here. So RT is a vector, right? So I can convert this vector into a matrix form. That matrix multiplied by some vector will be equal to that vector crossed with that vector. So I'll argue that like, this is basically just equal to, let's see, T cos our transpose, something like, let me make sure it's correct. Let's see. But yeah, I should have the transpose on the other side. So what's that? So because let's think of like if I have any vector here, if I have any vector, if I have RT cos times vector y here, so for any y here, this is basically it's just RT cos y, right? So RT as a vector, then cos with y. But now you think of like, I should have this vector. I can also obtain this vector as T cos R transpose y, and then R something like this one. So why is that? So think of like if I am trying to rotate, so I have a vector T here, right? Now I rotate somehow to RT and then make a cross product with some guys here. So and then I very hard to draw like 3-dimensional. So maybe like, so this is a RT cross, this is Y here. So and then wow, this is difficult. Let's say this is RT cos Y. And it would be the same as like if I unrotate this Y first. So now I have this coordinate like you can think of like I have T in one coordinate system. Now rotate to R this RT coordinate system, or like rotate to by R, the entire coordinate system rotate by R, and then cross with Y, and then you have this RT cross Y, right? Now, or you can think of like, okay, let's move the Y back to the original system of T. So then I will have R inverse Y, and then R inverse Y will cross with T here. Now the entire thing eventually I will rotate again. That should be equal to the original RT cross Y, right? And of course, for rotation matrix, our inverse is just our transpose. Therefore, I have like RT cross RT Y here is equal to RT cross Y. And so therefore, like, because for every Y, I have this is equal to this, right? So therefore, I should have RT cos is equal to RT cos RT here. Oh, because like this guy here is just equal to T cos times RT Y, right? Yeah. So therefore, like this guy here is basically just equal to this one here. So now I have something like that, right? I have something like that. Then now go back to my original essential matrix, this one. So I may write this essential matrix RT cos as RT cos. Let's see, how do I do it? Oh, okay. R transpose R, right? So now I think of this thing here as my new T pi here, T pi cos here. So I have like, instead of like R T cos here, I have T pi cos R here. But like I have this earlier expression here, like T cos, this guy here is exactly equal to RT cos, right? So therefore this is actually equal to RT cos, or like this T pi is just equal to RT here. So therefore, like if you see books that like in the other formulation, like expand like this essential matrix as like T pi cos times R, here know that like this is okay, both are correct, but the R are the same, but the translation here, like in the other representation here, like the T pi here is actually equal to the RT in our notation. So okay, that's just a remark, like to elaborate what we talked about last time. So now let's start with the new material we like to talk about. As we mentioned that like previously, we're going to talk about some machine learning and deep learning now. We'll move into a new topic. So it will be the last topic. And so actually for some of these materials we have covered like in this course, and actually all, basically everything we have covered like have been like studied for quite a while, like for several decades. So we mentioned like this edge detection, and we talk about some technique for WANSEC. If you remember, like using WANSEC for fitting. Actually, I used to remember because we have this extra credit in the homework assignment. We talk about SIF, and then actually did we talk about linear regression? Yeah, probably not, but we'll talk about that. There's some clustering, like we didn't spend time on that. Like PCA, we also didn't spend time on that. But like image filter, we spent some time on that. But this basically is like same thing, right? So it's like I shouldn't say same thing, but like SIF is like one kind of local kind of like very representative like image features for to represent images. But I shouldn't say images, but represent like some extract some distinct features from an image. Now, but like if you look at like more recent research, like if you go to computer vision conferences, basically like everyone are working on something like convolutional neural network, recurrent neural network, autoencoder, and so on and so forth, like or like multi-layer perceptrons. So this it sounds fancy, but actually it's a very simple things that okay, we spend some time, like maybe an hour today to just give an introduction, then on kind of like neural network in general. And there's a buzzword that you heard people like talk about a lot, like deep learning. So it's actually really just neural network. Uh, and neural networks is not new. I will cover some of the history here very briefly. Um, and you see, like this is like some old idea, then like people suddenly find it very useful, and then like kind of like become a really hot research area now. So it's good to study old stuff. Like I mean, you don't know when it will coming back, like to be very useful. So okay, so uh, first of all, like as you know, like for neural network or deep learning here, this is like really a sub subtopic of machine learning, and so really a subtopic of machine learning, and so maybe I'll just quick introduction. Or maybe I have slides for that. So let's see about that. So okay, let's go for some applications first. So but maybe just uh um some terminologies here. So because I may forget to talk about that. I don't know whether the slides have that. So you always like look see like there's several different terminology people talk about a lot, like say supervised learning and unsupervised learning. And we have like classification, like something like and regression, I say, as people talk about a lot. So first of all, like you think of like maybe I guess I would do a kind of I would say a participation like question here, just like so how many of you like know the difference or like know what's this terminology here, like kind of like you know what supervised learning and unsupervised learning, like from other class or like you learn it yourself like somehow. So I have some yes and some no here. Okay, actually many no. I guess and some yes. So I guess um basically like yeah I have many yes and some no. I guess half almost. So oh now we got more yes. So um basically like if you maybe I start with like what machine learning try to do. Oh, actually, I think I have some slides. Then I will jump back here. Like that's probably give a very good motivation. Let's wait a second. It's okay, here, yeah. So if you are in the computer science background, you must have like taken a class in like algorithm, right? So on, like. And if you're in a class algorithm, like you see like they have algorithms, probably like the first course or first couple lectures, like they will talk about like sorting, right? Something like, and you think of I have some kind of problem. I just want to sort a bunch of numbers, a list of numbers, and then like we design some algorithms to do that. Like for example, we can do the simplest bubble sort there. So we just okay, if I have a list of numbers, maybe I make it like I want to sort that like ascendingly. So what we can do, maybe we take a pair at a time. If one is bigger than the other one, then we'll just not in the right order. Then we'll just swap them, and then I repeat that like for every pair, and then repeat like many times. And for many problems, like but also like for only some problems, we can do something like that, right? We define precisely what the problem. Like my problem now is like trying to sort a list of numbers. Now then we think of like how we can derive some kind of algorithms that is always able to tackle this problem. So then like we can translate that into code to write the program, write a method, write a software, just define a function. So and then try to fill in the rest. Like so for example, like here, I also can have like very well-defined problem here. It's just some kind of classification problem. But this does not fall into this classic uh, algorithmic approach, um, algorithmic solvable problems like the sorting here. That, for example, if I try to classify like images, I have apple, tomato, like cow, and then like say I want to just have a function here, and I see this image, and then I try to just return the class label. Now it becomes very not obvious how we are able to do that, right? So how can I really write the program to decide that, okay, this is an apple? So maybe I need to have some kind of subfunction to say, okay, I should find a circle here, but then it's still like not clear, right? So uh, maybe I have like 2, 3 apples here, like one occur with another. If I just look for like kind of like circle, like then maybe like, and also like maybe it's not completely circular, or maybe I cannot define the edge precisely. So in any case, it's very difficult to define a well-defined algorithm, or not to mention to write the code to solve this kind of problem. So instead, like people look for this kind of data-driven approach. Is that like I don't know how to do it. So instead, I would just like create examples. The example would be just a database or a data set. So now I have like image one, and my corresponding labels would be apple. Image two corresponding label would be like tomato, and so on and so forth. Now I just give this list of examples to the computer, or machine learning algorithm, and then trying to learn from this data set. And what this did, like eventually, if you think of that in high level, is nothing, but it's just trying to fit a function, right? So you can think of like a very complicated function here. This function will just input an image. So maybe like image size like 512 by 512 here. And then it's going to like spit out the label here. And I with this example list, I'm just simply trying to create this function, or trying to fit this function. Very often, like this function will be parameterized somehow. So, or you can think of it, maybe it's not as obvious. But if you think of like really like for almost all machine learning model, you can just think of it's just some function that can be parameterized by some parameter here. And what we did is like we just vary this parameter such that like we can fit this function as fast as possible with our example list here. Um, and this is a supervised learning in the sense that like I'm giving you this example list here. I have a precise problem that I know uh for a given input, I know precisely what's the output, or like what's the label here. Now for unsupervised learning is that like I don't actually know the labels. I just give you a list of examples here. I give you a bunch of images, but I don't tell you like which is which. Like this one is an apple, this one is orange. I don't tell you any information about that. And I'll just let you to figure out like how you're going to use that. So maybe you are doing actually in the traditional sense, like many people consider this kind of clustering um, as a unsupervised learning. If I go back to the earlier slide here. So we mentioned that some of this like k-mean, or like PCA is, if it can be think of some of this clustering problem. So in the sense is that you give me images, like for example, I give you lots of images. Now I don't know I don't give you the label, but what I can do is if I look at the image space here, so each of this point now, you can think of it as an image. This is of course, it's just showing the 2D, but you can think of kind of imagine in the high dimensional, like very, very high dimensions. So each of the points here can be one image as well. And then for images, they look similar to one another. They will be like clustered together, or in the sense of closer together. Now then, we can try to have images that are close together. We can cluster them together, and then images far away, I will consider as a different cluster. Then we don't know the label precisely, but we can infer that okay, images like this one probably belong to one class, images for this one belong to another class. And once we do that, maybe if we just give one sample, like let's say I already cluster this here, now I give you just one sample here of the image. Let's say this one is cat, then maybe I can infer that the rest of them are also cats as well. Of course, this is super ideal, but this is the main idea of some of this one-shot learning, like people call it one-shot learning. Is you just give one label here, just for just with a list of examples here, but I just tell you okay, this one is a cat, then you're trying to do classification, more or less like this. So um and okay, I guess I kind of explained what was supervised learning and supervised learning here in summary. So supervised learning just you have label with label, right? And this is really just fitting function, and then this one is without label. So I don't give you the labels, but somehow hopefully you can still do something with that. And this is pretty vague in the sense that you can think of supervised learning as very much precisely defined problem. We know precisely what we're trying to do, but unsupervised learning, many people have different idea. Some people think of clustering. Some people think of you can be doing some kind of self-supervised learning. Um, I may have time to go a little bit more on that, but maybe not. So, but anyway, um, now how about this? Maybe another participation question. Anyone knows I mean, or I shouldn't say anyone. Just a couple of poll question. Uh, are you familiar with the difference between classification and regression? So I have some yes and some no here. Someone say a little bit. Um, yeah, you um actually it's important to know that whether you know something or it doesn't matter you don't know something, but it's good you have a sense that okay, I actually really uh understand the concept there. So that's the because that's impossible to know everything, but um it's good to know that okay, yeah, I don't know that, maybe it's useful later on. Then when I have time I'll get into that. So for this one, actually, it's very simple. That's nothing. Now we know what is supervised learning. They're both supervised learning. So the difference is just that you have here classification. You have a discrete label. You have a finite number of label basically. Finite number of labels here. Maybe I shouldn't say discrete, but yeah, I guess I can think of that discrete and finite number of labels. But this one here, regression is that you have continuous labels. So both of them are just supervised learning problems. So, but one you have the labels, you only have finite numbers. So you can think of, for example, very, uh, okay, maybe I give you another question here just to check whether you understand what I'm talking about here. So let's say if I have a classifier. Oh, by the way, like okay, that's very bad word here. So okay, maybe I have a machine learning model here. So what it try to do is to 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 differentiate whether an image, a picture, is a cat or not a cat. So it's like to differentiate. So now, is this a classification problem or like a regression problem here? Yeah, I know this is obvious. I even give you the big hints here. I say like, let's consider classification model. So anyway, so this, okay, this case, you only have two labels, right? Essentially, you just have two labels here, right? You have like, it's a cat or not a cat. So you have two labels. So of course, it's a finite number of labels, therefore it's a classification problem. So, okay, maybe, okay, even one, okay, maybe not asking that, but it's kind of obvious. So, and I will just give an example of regression. Like let's say if I try to predict the housing, predict a price of a house. So this will be a classic. I don't need to regression. This is example. It will be a classic regression problem. So I may have like different features here, like the size of the house, how many floors it have, how many bedroom, like how many bathroom it has, where was the location, and so on. And based on those like features, we are going to like predict the price, house of the price. Oh, sorry, what did I say? Predict the house price. So and that will be a classic regression problem. So these are the important concepts you should know about machine learning. So and don't get scared by machine learning and people call it data driven, like, or like data science, like all these fancy things, like all these ideas is actually very simple, like actually simpler than many of you has studied. In particular, if you study EE, it's more actually like more is simpler than like, for example, trying to understand Fourier transform and so on. Like this is a very simple concept really, and because it's data driven, um it's more like an art than a science, to be honest, because you see like later on when you eventually write the model and you try to train the model, uh, whether in converge or not, uh, that sometimes you relies a lot of experience, rather than like there's a very concrete math and saying, okay, this does not work because it's not really that obvious, even though like there's theory in machine learning, but oftentimes those theory have a very loose bound, and in practice, um, yeah, those theoretical results is not always, it's actually very, usually it's like futile, like for you to debug your code. So but it's still important to give you some insight. So if you have like some theoretical machine learning course, I don't, yeah, take the chance to learn those, like it probably is useful like in the long run. So okay, let's move on first. So here let's like to mention like this is a classic uh computation challenge, has been around like for a long time. So it's called a, I'm sure many of you heard of that. It's called ImageNet. It's organized by Stanford like for many years now, like over a decade. And it has in particular image classification challenge that have like, okay, this is not updated. I don't know how many images do they have now, but they have at least 1 million images, and they have 1,000 classes. And then like based on these classes, like they have like different outputs here. Like, for example, like I have this image here. I want to classify these images. And for your model, you're trying to, oftentimes you're going to like score, like for different classes, like how likely this image belong to each of the class. Then we can pull out the top 5 here. For example, this one top 5 is like we have like scale, t-shirt, steel drum, and so on and so on, so forth. And for this one, we will consider like if based on the top 5 uh, criteria, this will be a correct classification because I can pull out the steel drum here. And if for this one, if the model uh, output this one, like none of them like kind of belong to the, I mean, include the correct label, then we'll consider this as an incorrect classification. And for this classification problem here, classification challenge here, you can see like the winner over the years. This is a year 2010 by NESMU IUC, like this is 2012, like supervision. This is like by Jeffrey Hinton's group. And this is like Google led, of course, it's by Google in 2014. This is like MSRA is like by Microsoft Research Asia. And if you look at this one here, like this is actually what do you call that? A watershed here. Is a watershed? I don't know the English word. So it's a watershed moment. Before that, it's like using kind of like shallow. You can say like shallow model, or you can say like using non-neural network models. And after that, it's all based on neural network, based on so-called kind of buzzword like deep learning. And since then, every model beating the previous challengers or previous winners are all based on deep learning. Um, and also you can take a look of like this P deep learning model. Like you can identify some of these uh, things that you learn in class. Also, they use HOG like LBP. Like doing in any case, this is just extracting features, right? Okay, extract some features. Then we don't get into that, but essentially it's like also like some kind of extracting features, and then like oh actually, and then ultimately okay, you can think of like all these components are extracting features, and then you do a classification here like support vector machine, SVM and support vector machine. I'll briefly mention SVM also. Um, it's basically you can also think of this actually like a form of neural networks, but uh, it's mathematically it's pretty elegant. So and it's easy to train. So therefore, like it was very popular. It's still very popular, but it was very popular and considered the state of the art, like for during 90s and like early 2000. Um and uh and and maybe you can compare also the results here. So if you look at this challenge here, for before, as I mentioned, that this is like after deep learning, right? This is like P deep learning or P neural networks. So you can see like it's almost like people have kind of using like P deep learning or like using like shallow model have saturated like the performance. They cannot really push further. Like this is the accuracy, of course. Like it's trying to okay, this is a oh sorry, like this is the accuracy. This is the error rate, of course. So the error rate is pretty high, 28. And then next year we get a little bit back to like 25.8 here. Now suddenly like people come across like okay using like neural network models, and then they have a drastic like improvement, like decrease almost by 10% in terms of error. And then this is also like deep learning, like they change some parameters. It's like continue to get improve, and then like 2015 you get actually so well that like almost people consider this is like kind of solved problem. But I won't say so, to be honest. You will see why. Uh, okay. By the way, this human, like first of all, like this is actually one sample human, because no one bother to do that. But maybe you may try to do it like for fun. You have we have the 1,000 classes. I don't know whether I have that here. Let's see if I have that here. I can pull it up very quickly. Let me look for that just quickly. If I can find one missing, I can. I want to find the label here. Oops, let me take this thing away. Okay, I'm able to find that quickly. So let me. So this is the 1,000 classes. You can find that online. So it's not easy actually. If you look at that, like even human do it, it's not easy because the 1,000 classes, you have like something is quite like for example, thunder snake, like wing snake, wing like snake, like you know, because I'm not a native speaker. Like honestly, I have lots of words. I don't study like elementary school here. Like lots of words I don't know. I don't even know what is that. Like we view. I'm not even sure what is that. And mod. I guess you guys know this in elementary school probably. So I can yeah. So and basically that one human subject to do this task is like a graduate, like a famous uh, researcher now, like a graduate in Stanford. Like he just like for fun, try to like okay look through the entire list, and then he tried to like I don't know how he did that. Like he probably like group some of the similar, for example, because like this has a lots of cats and dogs, lots of different species of cats and dogs. So he categorized them together first, and then like he just look at the image and okay decide oh this is a cat. Then he go through the cat list and see like which one looks like is the correct cat. But even for him, like he do like only 5%, like is uh top five error like 5%. I mean it's actually a lot easy, like even for human. And this is like for classification, we can have like even more challenging problem. For example, like this one like object detection. So now for the image, inside the image, you have like more than one uh, object that you are interested in. So then you not only like you want to identify what kind of object it is, you also want to locate that. So I want to say, okay, this is a car. Like I want to like put a box there, and also I can with like probability one. So like I 100% sure that this is a car, and I can identify this as a dog here, a horse here, and so on. Um, and for object detection, like so also like people getting like much better now. This is a based on this mean average precision criteria. So I won't go into detail like how what does that mean, but like of course it's higher is better here. And it's it's getting like yeah, of course it's getting better and better over the years with the deep learning model. And we can even have like uh this more I mean, like for the object detection, you can think of like we just put a bounding box, right? But we can get even like finer segmentation of the objects. Like we have this typically known as a instant segmentation. So you basically want to identify the object of interest, but also you want to segment that out. So for each different subject, so you have a just for you want to identify the pixels like for that object. So you have a very so this is an instant segmentation by the way. This kind of problem is known as instant segmentation, and that's another very similar problem known as semantic segmentation. It's a little bit simpler problem there. So for semantic segmentation, like I don't separate uh, each object like in the scene here. So you can see like for this instant segmentation problem, like I actually managed to separate each of this object here also. So I know this is shape one, shape two, shape three here. But for the semantic segmentation problem, what it does is just say for the entire image, I will identify like for each pixel, like whether it's a pixel belong to a dog or like belong to a sheep and so on. So in a sense, like all these will be identified as a sheep pixels or something like that. But of course, I shouldn't say that usually instant segmentation is apparently is more challenging than semantic segmentation, but also like for semantic segmentation, you typically you're going to like classify for each pixel as well. But here, like you see, like for instant segmentation, maybe we won't classify the background. So even though instant segmentation is like usually more challenging, they are not really you cannot say like instant segmentation is strictly uh, a superset of the semantic segmentation. And also like we can use like laterals, I do a post estimation here. Say you identify each of the person in the scene there, and also like you also estimate the pose. And we can even do like this kind of like image captioning. You have each of the image coming in. I'm trying to like put in the label, put in the caption, so to describe what's going on in the image. So for example, like you have like some of this is pretty accurate, right? You have this boy is doing backflip on the wakeboard. Yeah, I'm not sure what's wakeboard actually. So and of course, I yeah you yeah, we may have time to go a little bit into this kind of stuff, may or may not. So um and this also has some dense image captioning, like identify each of the object here and also give a caption of that description. Uh, I'll give a description of each of the box as well. And we can also do like visual answer, question answering. So we give an image and then ask a question and try to have the model to answer the question. This typically is a very challenging problem. So because it's involved like several fields, you have like computer vision and also natural language processing. But with machine learning model, like it's actually not, at least it's, I wouldn't say a doable, like you won't have a perfect solution. So you have a solution that's kind of like working sometimes it's not working that well, but it's a baseline model, I guess. We probably won't have time to get into that though, because we with this, we also need to look into the NLP model. So we'll see about that. And also we can do super resolution. Like yeah, I won't go into that. Like so, this is apparent, right? So you just say from uh, lower resolution images and make it a higher resolution. If you remember, we'll always also briefly talk about that, like when we talk about upsampling. If you just do some cell processing in using like for example bicubic filter and so on, like you can get performance like this and compare with like saying doing super resolution using deep learning, visually it will be much better here. So but be careful though of like when you do like super resolution with like machine learning or like using deep learning, it's a data-driven approach. So what I try to do is like, okay, based off all the images it learned in the past, it believed that, okay, if I see, for example, I believe this is a parrot here, or I believe that, okay, here, like, so therefore the pixel like should be looks like this and so on, right? It fill in the missing gap from the data there. So therefore, like this is good for commercial application. For example, you have a camera, you want to do a super resolution, you just want to get an image. It looks good, right? But it probably is not a good idea to apply to medical images because you don't want to have from your data and people's data and basically the model will make up something. Okay, look at this one here and think, okay, I believe there's a cancer cell because it may or may not, but if it screw up, then it will screw up pretty badly. Or like because yeah, so uh at least at this moment, I don't think like this kind of supervised solution is like uh be used commercially like for medical images. Okay, maybe I'm wrong because I'm not, but I would guess like that would be if they use it like medical images like that, there would be a huge caveat there like to be really careful like to do that. So that's also like you can use, surprisingly you can use a deep learning to do like something very very interesting here is like generating art. You can say what's going on is like I have an image here. I can put in different style, like from other paintings. I can extract the style, for example, like for different paintings that I have different styles. Like this one, I don't know, like a famous, I don't know by who I forgot, right? That are like this probably by Picasso, like Starry Night. So you can extract the style here, and then you can combine this style with this painting or this photo here to generate a different image. Um, and this is another some other examples here. And this is a long at the deep dream here. So based on the data, what it did, so okay, at a higher level, what it did, that this deep dream is that it's trying to from the data enforce like, okay, I already have lots of data in my models here. You can think of like the data, so it's like your experience. So, and based on like what you see, like what you input into the image, you just like look at like different parts and you think of like from the experience, what does it look like? So you just like reinforce like what it look like. It's like dreaming there, like because you have that in your mind, then you just dream more and to reinforce that, like make it more like what appear in your experience, and you ended up with something like very interesting, like this one. Okay, I don't have ones that uh some of this deep dream always give you images. Everything is everything you look at, it looks like dog or cats because I actually especially dogs because I many data sets like contain lots of dog images. So um and also application outside a computation like have lots of application on natural language processing. Now it become like definitely the state of the art to doing NLP. Um, and I won't go into that like because this is not also like for gaming as well, like or like for uh yeah for gaming. I of course I guess many of you should heard of like AlphaGo, like the model that beat those world champions. Now like humans just like cannot compete with like machine on Go anymore. Um, Go by the way is a Asian like Chinese game that is supposedly is a very difficult game. Um, it's more challenging the chess and so on, but uh, yeah, people in the past, I just couple years ago before like with the AlphaGo model, like people thought that like we need at least like a decade more to have the machine models to beat human, but it's just like yeah. So anyway, like all this make human species humble. We are not as smart as we thought, I guess. So I spent quite a bit time. So I just give this introduction. So I will see like how far I will go here. So first, like I guess like a little bit for fun, like after all, if you think of the neural networks as the name suggests, it's really inspired by our by the brain of our own brain, right? So a little bit statistics of our brain here. So the average weight is like 1.4 kilogram, is only 2% of the total body weight. But actually it consumes quite a lot of energy. It consumes like 20% of our energy. And but it's still like it's actually very efficient. It's like only 12.8 watts. So if you think of that, it's less than my laptop, right? My laptop's like power, I don't know, but yeah. It's like maybe like 50 walks or something like that. If you think of GPU servers, like nowadays it's probably more efficient, like, but uh, still like you a TPU GPU servers, like you use the power is over 1,000 watts, and so you can see like how efficient is our brain. It's actually super efficient. Um, and we basically our brain and also our neural system is just connected. It's just composed of like neurons that interconnected with one another, right? So biological neurons will be like that. We have this dendrites and like nucleus and axon and so on. So, but the main idea is that just you have this dendrites is collecting like chemicals, and then when it's collected sufficient, it got excited and then firing to put this axon to the axon ending, and then at the ending it will generate more chemicals. Then it will kind of excite another neuron, so, and then I or like multiple neurons, and then they continue to pass. Um, and so we'll just simplify this model to simplify this biological neurons to a a very simple model here. So of course it's very imprecise because when these neurons are activated, they pass this signal here. The signal is not okay. You see here the signal I have here for this artificial neuron is more or less just like uh, okay, depends on your activation function here. Uh, it, anyway, it's just will be a scalar value. It will be just a some scale value here. But by the way, like for the original neuron here will be a dynamical model because when it activated, it will send a sequence, something like I forgot how people call it, say a time code or something like that. Like so, um, basically, like if you activate is activated, you will send like a very fast kind of like signal here, like very dense signal here, like close to one another. But the magnitude will be more or less the same. But if you're not activated, like maybe you will send something like not as kind of like densely packed signal together. So, but anyway, let's go back to this artificial neuron. So what it is, okay, to try to model that is simply you can think of like each of this input here is like you getting chemicals like from elsewhere, right? So you have like multiple neurons here, you're getting into that axon ending here, and then you have another neuron. You can collect from these neurons or collect from this neuron, right? And then you collect some signal here, and this signal like will be weighted. So each of these neurons like may have different effects on these target neurons here, and I'm weighted and I'm sum all of this together. When it's sufficient, when this sum is sufficiently big, like larger than some threshold, you will send some signal. So at least this is like the original idea. So therefore, like this activation function, like in the past, like they would just like put in like for example like step function here. So if like this sum is like sufficiently big, then I will just have a signal one here, otherwise a signal zero. And you can interconnect many of these neurons together, and this is like people known as like the multi-layer perceptron. But later on, like people just extend this idea. So basically, we don't really always need to use this step function for activation function. So then people like later on smooth that out, become a sigmoid function, and later on they even change to many different functions. For example, just use a this kind of like linear semi-linear function that they call it like rectified linear unit. How to spell that? Rectified linear unit, or short for just valued. Um, so and then nowadays people have like different activation functions here, but Valute is very common. Like if you build a neural network yourself, like you may start with valute. And depends on applications, and maybe people also use like 10H here sometimes. Um, and there's other like activation functions as well. So this is about electrical neurons, or sorry, artificial neurons. Then you put them into a network together, then you have a neural network, as simple as that. So and I can have like, okay, typically people will arrange the neural networks into layers. So I can have like just a single layer, single hidden layer here. I have input coming in, pass through one layer of hidden units, or like one layer of like neurons, and then this layer will again collide to an output layer. So we call this middle layer the hidden layer, hidden, um, yeah. And then in this case, it's a single layer neurons, neural network. You can consider this is a single layer. And yeah, actually, why I call it single layer, I'm not so sure. Like maybe, yeah, but it's okay. Like don't bother too much with these terminologies here. Uh, so and of course I can or single. I guess it's better name it, but single um, a neural network with single hidden layer. That's probably better, more precise. And I can also insert like multiple hidden layers here, right? And actually, typically, that's what people refer to as a deep learning. Is like you, it's really just a neural networks with multiple hidden layers here. Um, and okay, okay. Let's see. Let's look at like a brief history of like ANN here. As I mentioned here, this is super brief, by the way. So neural network is not new. Like people think of the artificial neurons like for many decades already. Like back in the days, like last century, like in the 40s. So they have this perceptron. So as I mentioned, this perceptron is nothing. It's like just artificial neurons, but they have the activation function here. So I just use a step function. They use this as a artificial neurons, and they connect them together. They call it perceptron. And if you have multiple layer, you call that multi-layer perception and so on. Um, and there's a book like called Perceptions, like by Marvin Minsky and like Simon Pepper, like published. It's a very influential book. And there's some criticism of perceptions on all this. And in the perception model saying that like some function they um cannot emulate. But by the way, like that criticism is actually is not entirely correct, or like they have a footnote there, have an assumption that based on that assumption you cannot model everything. But usually people not very careful with the fine pin there. And also like because the area started in the 40s, they started with lots of hype. Like at the beginning, people think of okay, we can create a brain, like they can do all this classification, like and so on and so forth. Like people even think of okay, I have like 4 layer of neural networks, like with 100 neurons now, I can classify a tank or something like that. There's lots of outrageous claim like at the beginning of the early history of this artificial neural networks. So therefore, when people like have a rigorous criticism like that, ANN just lost favors. So that's like more or less a first winter of like I'm also actually like of artificial neural networks. In general, also like AI is losing kind of favor as well. And actually, or like I shouldn't say that. Like people move into like expert system and so on and so forth. Like lots of search and so on and so forth. Um, and then ANN like get back to favor around 80s and up to maybe early 90s. Uh, and because there's a popularization of this backpropagation algorithm. So this is not new. Actually, if you, as you will see, like this is nothing, but it's just calculus. It's just chain rule in calculus. But people we discover that like many times. Probably like the form we know now is probably like uh, first invented like during 70s, but then it got reinvented several times and like got popularized like in the 80s. Now before that, like people don't know how to train neural networks precisely. They train it pretty ad hocly and didn't do well. So now they have the bad pop. They get a little bit better in training, actually quite a bit better in training. So and again, lots of hype getting in, and then like yeah, also like lots of claims and so on and so forth like that. The area get hot again, but again it lost favor in the 90s to support vector machine. Um, and it lost favor because SVM is more elegant, like mathematically, and it's easy to train. Uh, it's very robust in the sense you know what you get. Basically, you know precisely what you get. You know your expectation, and so like uh, basically people move to the SVM camp. But as you see also like SVM is nothing. It's really a single neuron model. You can imagine that it's just a single neuron. Um, then in the mid 2000, there's some success in deep learning. So in the sense that in the past, people also like think of, okay, I don't train well, or like I cannot um my model is not doing so well when I only have like a one layer neurons or like a couple layer of neurons. Lower laterals doesn't do well, so I probably should go for a deeper laterals. But when they have a deeper lateral, they don't know how to train it well, and they always fail to train that. So until mid 2000, people find some tricks to train deep neural laterals, and suddenly like they find that like the deep neural lateral models is able to beat many prior machine learning models in many problems. Then suddenly like neural laterals just have a major comeback. In particular, in 2012, we have the ImageNet moment that people like before that totally don't know what's neural network like for, or like it's a simple concept, but like it's pretty new suddenly because like it's an old idea, but people didn't study for a long time. And then yeah, they just suddenly like they see the results, then everyone think that oh, I need to study that. Then now they like everyone is working on deep learning more or less. So I want to say, okay, I probably have like enough time maybe to talk a little bit SVM. I guess uh it's a kind of still important because as I mentioned, a support vector machine is very easy to train, like and give you quick result. Basically, you don't need a GPU to train SVM, and you have like relatively good result as well. Of course, it's not competitive like with compare when compared with like deep learning model. So I'm also like it's fair for me to talk about that because as I mentioned, you can really imagine SVM is nothing but a single neuron model. Is really what the classic SVM model is, just doing a binary classification with a single neuron. So I have an input here. For example, I can think of this input as a cat image here. I'm trying to classify whether it's a cat or not cat. Then I just put each pixel into this input here. Then I will just use this single neuron and weight the sum together. Then I will determine, okay, whether this is a cat or not a cat, right? So I go for this activation function. This activation function here will be just a step function now, right? And if I got one here, I will just say, okay, it's a cat. If I got zero, it's not a cat. So now then, if you then think of that, like it's really just a linear classifier, right? So I have, for example, this is like representing a 2D space here. So I have maybe this is a data points here, data I have like this is one class here, this I have another class here. Now what SVM trying to do is that, okay, of course I can classify these two by putting any arbitrary like linear boundary here. Let's say I train the model now. Let's say I have, this is my input data here, right? This is my input data. Now based on this input data, I train a model to have this linear boundary here as my model for my model. So basically saying that like now if I have any data point on this side, I'll classify as cat, and on this side I'll classify not a cat, right? Now I can have like lots of this boundary, like we'll be able to fit for this data here, right? But apparently, intuitively, I would say that like my best boundary will be boundary like this, right? I try to create a margin here. So let's say if I create a boundary here and think of the point that's closest to this boundary here, and I will call this gap here as a margin here. I want to have this margins here as big as possible, right? So if this margin is as big as possible, then probably it's the one with the widest margin will be the best model here. And this is the basic idea of SVM. And by the way, like why we call like SVM support vector machine? Actually, I don't know why it called machine, but it's like why we call support vector is that like this point here that's like closest to my boundary here is known as the support vector. And it turns out that like your model itself will only depend on the support vectors, and you ignore all these other data points essentially. So, and the support vectors therefore is very important. Now, if I go back here, I can easily model this into a very good, very well-defined mathematical problem or optimization problem. Now, I go back to some of the geometry or like, yeah, I guess it's geometry maybe. So think of like I have a vector. This is okay, let's say I have this boundary here. This is a boundary. And let's consider this vector here perpendicular to this boundary as W. And apparently the line here, I can write down the line equation. So like actually in high dimension will be the plane equation for this boundary as a W dot product with X. So maybe I represent this as my dot product. X is basically some points in the space, any points in space. W dot X, or I should say, let me say that. Like, so every point on this plane should give me W dot X, the inner product of W and X should be equal to some constant, right? Maybe I just write K here, some constant K here, right? So if I have this is like the W vector here, right? This is the W vector. So I have this vector perpendicular to this plane, and W dot X is just the inner product with this W vector here. And so every point on this plane should be just a constant, right? I mean, every point on this plane should have like W, the inner product to be a constant, right? So therefore, I can just write this equation of Wx minus b is equal to 0. Now I just move, actually, or I can now really write this as b. I will write Wx minus b is equal to 0, like that, right? So if you look at another plane, like parallel to this boundary here, let's say it's this plane here, like hitting this support vector here. So I should have like Wx minus b equal to, let's say, another constant, maybe I call it like c this time. And I should have like, let's say, this here on the opposite side of this plane here should have like Wx minus b equal to, let's say, minus c here, right? So if my boundary is exactly in the middle between these two boundary here, so I should have like one is c, one is minus c, right? And by the way, because my W here, I didn't say like, okay, by the way, I can, okay. I can just normalize like both equation here by C here. What I mean is I can divide everything by C here. So this is C, W over C, W over C, B over C. So then I can have an equation instead. Like for this one equation is like wx minus b equal to 1. Of course, I should have a different w now, maybe w pi or w pi x minus b pi equal to -1, where my b pi here is just my original b over c, and w is like original w over c here. So, but anyway, like, let me just ignore this pi here. Just basically, I can always, therefore, like think of like this two boundary equations should be like wx minus b equal to 1 and wx minus b equal to -1. So now what's the length of this gap here? The length of this gap will be simply, if I think of I have a point here, let's say I have a point x -1 here, and I have a point x1 here. If I consider a vector here, let's say this vector like from x -1 to x1 here, if I use a different color here. So then the gap here will be simply equal to the projection of this vector to the w direction, right? So, or in other words, it will be just equal to x1 minus x minus 1 project to w, right? So this will be the gap, the size of the gap, right? So note that like, I need to normalize w. I would be like this, kind of like, I don't know how many of you remember, but I guess I mentioned that like kind of like in one of these other other lecture here. So if you have a vector, basically I have a vector here. If I project this into another vector, let's say this w here, the length here will be just equal to x. Oh, by the way, this will be okay. Maybe okay. The length here, let's say this is called theta, right? I'm sure you see this before, but maybe just refresh your memory here. So this will be equal to x cosine theta, right? And by the way, x cosine theta will be equal. And by the way, like what's w dot x? W dot x is equal to x log times w log. Maybe I should write the x log times cosine theta, right? So therefore, like this length here, x cosine theta is equal to w dot x over w. Yeah. So that's how we get this one here. The gap is equal to this one here. So, but then like this one is equal to 1 over w, right? And w x1 here minus w x minus 1 here, right? But wx1 here fall on this line here, right? So therefore, I should have like wx1 is equal to, okay, maybe I really should pause. I have a, but if I, okay, let me just pause here and give a question, then maybe like end here. So what is wx1 here? Given that I have wx1 minus b is equal to, oh, I have already say it out loud. Given that like x1 fall on this equation here, so what is the question? Like what is wx1? So note that x1 fall on this line here, and x minus 1 fall on this line here. It's close, but you have to be careful here. So I guess that many of you already not here. So I guess that's, so okay, I guess I will just give the answer. So x1 fall on this line here, right? So therefore, like it should satisfy the equation, right? So therefore, I should have like wx1 minus b equal to 1, right? So that means like wx1 is equal to 1 plus b here, right? So therefore, like, okay, let me just quickly finish that, and I will. So I have like this is 1 plus b here. I can argue the same way because this satisfies this equation, right? Minus 1 plus b here, right? So then I have like b here cancel, so I will just have 2 here, right? So this is just equal to 2. So therefore, the length of the gap will be simply 2 over w. So now then so what we have is like essentially we want to minimize maximize this gap, right? So maximizing this gap will be just minimizing w here. So I will come back to this next time. So I will yeah, I will see you guys next week then. Yeah.
I have a question
Yes.
actually. So it's just some advice for the final project. Me and my partner are actually doing a classifier in which it's supposed to detect different kinds of animals.
Yeah.
And our biggest our biggest challenge so far has actually just been getting like the sheer amount of images we need to train the
Oh,
classifier.
okay. Yes. Wait. You don't want to prepare. I guess when you guys submit the proposal, like when you say that you're going to collect data, I remind some of you guys I don't do that because you can spend like many days and hours just do data collection, like, and it's not something you want to do.
Right.
So you want to, okay, let me pull up a why I cannot, that's so difficult. Uh, for some reason, like my laptop is a little bit slow. I'm not okay. Now it's okay. So um, so one thing is that you may try this something like for example, there's a Google has a data set search.
Okay.
You can start with like animal images, maybe, uh, and then just start from there. So
Okay.
don't try to, yeah. And or you can also search in Kaggle, but I guess you can just use this Google's data set search because um yes, and it connect to Kaggle anyway. So if you go for Kaggle, of course, it's a competition site that like lists lots of competitions. They usually have like lots of data sets also. You
Right.
can browse those. Yes.
Right. Yeah. Because like we're using a HAR cascade classifier, so we have this like surrounding code to make it work. It's just we have to generate the XML files uh, to finish the project.
Oh wait. So you mean you need to generate the labels or like
Um,
are you
it's
doing? Okay, wait a sec. You're doing a classification or a detection problem. In the sense that do you localize the uh, target as well, or like you're just trying to like classify that?
we're we're just trying to classify it. So given an image, we want it to tell what kind of animal is in the image.
Yes, I guess you probably want probably want to look at the data sets first. So if your data are unlabeled, then yeah, definitely, yeah, you will spending as much time like trying to just label your data.
Right.
So you definitely don't want to spend time on that. Yeah.
Right.
Yes.
Okay.
I'm sure that if you do something like that, you can easily find, for example, like just go to ImageNet, like they have label data, right? And if you look for ImageNet also, uh, they are basically just classification problem, right? So if you just on ImageNet, of course it's huge, and you don't yeah, you may want you probably just want to like train a subset of ImageNet because it's huge. Yes.
Yeah. We were actually looking at that site and we weren't sure how to navigate it or use it properly. To be honest.
Um. Yeah. I guess that you okay. Uh. Try to yeah. That's the pre-processing. Like always. Uh. It's case by case. Because unfortunately I don't really have a really precise advice because oftentimes you go to the data set, some of them they work well, like
Hmm.
it's always just like pulling code online. Some of them are very well documented and actually will work. Some of them doesn't explain as well. But of course, if you and also like um uh another thing like you may do is simply like if you search for torch, let's see. Um okay, I can't suddenly forgot. Like, what's that called? Uh, oh yeah, I think there's something called. Oh, but that's is kind of annoying also fast AI because the documentary is not. Um, so that oh yeah, that's oh okay. You can also like try to look for fast AI. They are basically I'm not sure you heard of Torch and PyTorch. So PyTorch is something like to build neural network models. Uh, like based on the original torch now they kind of like port it to Python. They call it PyTorch. And fast AI is like a plug, like I shouldn't say plugin, but like something like a layer on top of that, like trying to make it more simpler, like a high level. And they they have some functionality that you can pull out some of this data set directly using the API. So
Hmm.
uh, that one is like you may uh, or like you may even like just go okay. Let me just Google quickly. Uh, oh okay. Actually, some common data, like for example, if you look at like all these packages, like for example, PyTorch, TensorFlow, and they have some load data loader, like for some common data set, like for example, like let's say maybe I search right. This may not be a good one. Um, oh, okay. That's maybe need to go into the code of. Yes, for example, like this may that you can take a look of like example like this. So they already have like some functionality that like you can okay, of course, okay, this I guess you still need to download the data, but this allows you to load the data there that like is kind of like already organized the labels and so on.
Hmm.
Yeah, that you don't need to bother with like the XML and so on. You don't need to go into the low level. Um, I think like fast AI have even more refined uh, API for that. I played with that like a year ago, so I don't have like I forgot most of it like on top of my head. But I'm also like another issue is like for fast AI though is like it it developed quite the documentation I was saying is not as well um kind of like documented like as in PyTorch and so on.
Right.
So sometimes when they upgrade the versions, some functions they change it, and then like they didn't document that. Like you need to Google quite a lot. Okay, this doesn't work, and usually you will find the answer like after some Googling. But
Right.
yeah, so but I would say like don't go low level. Like if you need to label stuff by hand, or like even like you have some like well-known data set, if you need to, you find that you're kind of playing with the XML there, probably something is wrong. Someone already definitely have done that before. You can, there should be some API if like well-known data set like ImageNet and so on. Like um, you should be able to find example online. Like just pull out the data and then train it directly. Yeah.
Okay.
Yes.
Okay.
Yeah.
May I also ask a question about the homework?
Yes.
Okay. May I share my screen so that you can
Oh
see
yes.
my?
Yes. It's like I yes.
Okay. Let me. Okay. So this is the first problem, and to my understanding, you